De acuerdo. Buenas tardes, soy Andrés Castellanos. Voy a actuar como presidente de este comité de evaluación de tesis y voy a dar apertura al acto académico que es la defensa de tesis doctoral titulada Optothermal Studies of Heat in Van der Waals Materials, que será defendida por David Saleta con su supervisor de tesis, el profesor Klaas-Jan Tielrooij. Voy a presentar a los miembros del comité de evaluación de la defensa. Tenemos a la secretaria María José Esplandiu, que es de aquí de ICN2. Tenemos en remoto al profesor Eric Pop de Stanford, que ha madrugado para acompañarnos esta tarde. El acto de defensa consta de una presentación que dará el candidato de entre 30 a 60 minutos, dependiendo de, bueno, más o menos, ¿sí? Y será seguido de un acto de defensa con preguntas y respuestas con preguntas del comité, respuestas del candidato, a lo que continuaremos con una evaluación a puerta cerrada los miembros del comité. ¿De acuerdo? Me gustaría recordar que el acto de defensa de tesis doctoral es un acto solemne, es el título más elevado que permite otorgar la Universidad Española. ¿De acuerdo? Es un acto de defensa, lo cual quiere decir que al final de la presentación del candidato todavía no aplaudiremos porque no es un seminario, esperaremos al momento de deliberación del tribunal a que demos la calificación. Una vez que tengamos la deliberación y demos la calificación, podremos dar la calificación desde no apto, aprobado, notable o excelente. La evaluación, si consigue la nota de excelente, podrá recibir una evaluación de cum laude que se emite en voto secreto y recibirá al candidato en un email unos cuantos días después de este acto de defensa. Y si no me he equivocado en nada ni me dejo nada en el tintero, creo que podemos dar comienzo. From now on, I think like the committee members, we will switch to English because like the thesis defense will be English. We have an English committee. I hope that you can all follow. It's also for you guys, family and friends as well. So thank you. You can go on.
Thank you very much, Andrés. So for the last 5 years, I've been studying heat using light in two-dimensional Van der Waals materials. So why is it important to study heat? Well, first of all, most of the energy we produce worldwide is wasted as heat. So waste heat is a big problem in our society, or we use it for active cooling. And this means that we need better heat management solutions. And with this, I don't mean we need better fans to cool our laptops. I mean that better understanding of heat transport at the nanoscale is crucial for continuing with technological progress. Eventually, better understanding how heat flows at the nanoscale would allow us to better control heat and eventually will have massive implications in our society. So why would we use 2D materials to study heat at the nanoscale? Well, let's start from the basics. What are two-dimensional materials? These materials are made of atomically thin layers which have covalent bonds in the plane and are held together via weak van der Waals interactions. This means that it is possible to produce atomically thin flakes that can have one or a few layers, a few atomic layers. So these are materials with sub-nanometers thickness in the monolayer and one or very few nanometers in the few layer regime. So these materials are strongly anisotropic. It is not the same to look at them from the side or to look at them from the top, as well as it is not the same for heat to move within the layers or across the layers. In this talk, we will refer to these two directions as the in-plane and the out-of-plane, and we will try to study the thermal properties in both of these crystal orientations. So nowadays, we know plenty of two-dimensional materials with all kinds of properties, from insulator to superconductors. And in particular, we chose to study transition metal 𝐒𝐭𝐿. And these are semiconducting two-dimensional materials that have three heavily investigated functionalities. The first one is for logic computing. So as these materials are atomically thin, it makes sense that chip manufacturers are already considering them to further miniaturize our electronic components. The second one is in photonics, where monolayer transition metal 𝐒𝐭𝐿 are direct bang up at the monolayer limit. These materials support strong excitons even at room temperature and are easily controlled using external stimuli, which is advantageous for device control. The third one is in neuromorphic computing. And here it's where people are trying to make computer chips that process information more like a brain. So receiving additional stimuli for functionality. All these applications would benefit from a better understanding of heat transport at the nanoscale. So this brings me to the outline of my talk. We will first start by introducing how heat flows, both at the macro scale and at the micro scale. We will see what was known and what was not known at the time we started our research. Then we will fabricate two sets of samples, which we specifically designed to perform two kinds of experiments, where we use light to study heat in the in-plane direction and in the out-of-plane direction. For in-plane heat transport experiments, we will use suspended samples and Raman thermometry. For the out-of-plane heat transport experiments, we will use time-domain thermoreflectance, and we will also explore the possibility of coherent phonon heat to occur in these materials. So let's begin. Typically, heat flows from hot to cold regions. And in the macro scale, this is characterized by a diffusive process. The microscopic heat carriers move across the lattice, eventually scattering with defects, other particles like other phonons. And at the nanoscale, well, let me say that the average distance these phonons travel before a scattering event occurs, it's defined as the phonon mean-free path. And at the nanoscale, the size of these systems is so small that the system length is comparable or smaller than the mean-free path of the system. This means that these phonons travel freely, and the first thing they encounter to scatter with is a system boundary, so a surface. This is characterized by a ballistic heat transport regime, and as heat is carried by multiple phonon modes, each phonon mode can have a different velocity, so they can move at different speeds within the crystal. So what was known when we started our research? First of all, we knew these materials are strongly anisotropic, so they propagate heat very differently in the plane or across the plane. The thermal conductivity of both TMDs is 10 to 20 times larger than the out-of-plane thermal conductivity in these materials. And what happens when we decrease the thickness? Well, for thinner flakes, typically we study them in suspended sample configuration, and this is because we don't want to have interactions with the substrate. We want to make a thermal gradient where the heat only flows within the plane in our crystal. The thermal conductivity slightly decreases when we make our materials thinner and thinner, and this is also the same in the out-of-plane direction. For the out-of-plane heat transport experiments, we basically use supported sample geometries where we place our material on a substrate which will act as a heat sink. So we can define a thermal gradient from the top to the bottom of our material. A very important work in this direction is this paper by 𝐒𝐻𝐭𝐻𝐿 and Reig, where they report size effects manifesting as a quasi-ballistic heat transport. Importantly, when we go to the atomic scale thickness, we have much better importance of the interfacial thermal conductance. It's not so important how heat flows within the materials, but how is the contact with our adjacent material, being a substrate or anything that is in contact with. The interfacial conductances for 2D materials with 2D materials is a bit smaller than that of 2D materials with 3D materials, and a bit smaller than that of 3D materials with 3D materials. So what was not known when we started? Well, first of all, it was not clear how the material thickness would influence the thermal properties of these materials, in particular, going down to the monolayer limit. So layer by layer, thinning it down till we have a single atomic layer. It was also not very clear how the environment would affect the thermal properties of these materials. These are so thin that they are very susceptible to whatever you put next to them, being a different gaseous environment, a different substrate, what you put in contact with. So it is very important how thermal transport properties depend on the environment. For the out-of-plane direction, it was also not clear how the 2D material thickness influences interfacial thermal resistance. And importantly, it was not known whether 2D materials could support coherent heat transport. And this is a transport regime where these heat carriers, our phonons, move like waves, and therefore we can produce interference effects and other means of control to our heat transport properties. So this brings me to the second section of my talk, where we will discuss the fabrication of our samples. Specifically, we will talk about the fabrication of our suspended molybdenum diselenide flakes, with which we transferred using a home-built transfer state. However, all the methods that we report in this section are also applicable to our supported samples. It is just easier because you don't need to suspend them in the air. So how do we produce our flakes? Well, we use mechanical exfoliation. So basically, we take a piece of Scotch tape and we start peeling layers of our bulk crystal. And this has led to the discovery or the demonstration of the electric field effect in graphene, which eventually led to the Nobel Prize in Physics in 2010 by 𝐿𝐻𝐿 and 𝗏𝑉. So we use this method, and basically we take this piece of tape with thin 2D materials and stamp it on a transparent substrate, which you see here. We use a transparent substrate because we will use it then for good alignment and a deterministic placement of our flakes on our desired substrate. If you look under the microscope, you can find these beautiful tiny pieces of atomically thin flakes. We take these flakes, we put them upside down, with the aid of a camera, align it to our substrate, and via stamping process, we transfer our 2D materials, in this case, over a circular aperture, therefore producing a suspended membrane of our atomically thin material. So this is, we make tiny drums. For this, we have used a home-built dry transfer stage, which is basically our camera with a zoom lens. We have temperature control here, thanks to a heater and a thermocouple. And basically, it's two sets of manipulators that we use for precise alignment of our flakes over the target location. In This design was inspired by a previous design by Andrés Castellanos, and it actually helped us a lot in our research. So we take this equipment and we produce a bunch of suspended samples. What happens? That sometimes they become wrinkled. Luckily, we found out by a simple annealing process that we can flatten these materials and recover their atomically perfect and flat surfaces. So we made several 2D materials, and these samples have, first of all, extreme thickness control. They show record large suspended areas, specifically for our monolayer flakes. These are sub-nanometer thin flakes suspended over 15 micrometer holes. So basically, huge suspended areas of atomically thin materials. We made multiple samples with 1 layer, with 2 layers, and with 3 layers to study sample-to-sample variations or the reproducibility of our experimental techniques. We then characterized these flakes, which I will not show in this talk, and we confirmed that they are single crystalline. They come from a single crystalline bulk material, and therefore they preserve high crystallinity. We used AFM on the suspended regions, and this revealed atomically flat suspended regions. This is not the case if you put them on a substrate, because these materials are so thin they will conform to the roughness of the substrate. Importantly, our samples enabled for the first time direct optical absorption measurements. So basically, we shine a laser, we measure the transmitted and the reflected power to estimate the absorption of our samples. And we'll see that this is a prerequisite for our next set of experiments where we study the in-plane thermal transport. These are our results. We see that the reflectivity increases monotonically from 2% at the monolayer to around 20% for 5 layers. And the absorption is about 10% for monolayer, going up to around 33% for thicker materials. We summarized our results in this technical note, which we published in 2021 in the Journal of Applied Physics Materials. So with this, we reach our third section, where we perform in-plane heat transport experiments in our suspended molybdenum diselenide flakes with thickness control using Raman thermometer. So how does thickness influence thermal transport in 3D materials? These are our conventional materials, the ones we use every day in our lives, like silicon, the one we have in our chips. So here it is clear that decreasing the thickness of our conventional materials produces a degrade in their thermal transport properties. And this is because we start having many more atoms at the surface as compared to the bulk. So our contribution from surface effects increases. We'll have larger phonon scattering at the boundaries, and therefore the thermal conductivity decreases significantly when we thin down our materials. So our question is, what happens when you decrease the thickness of a 2D material layer by layer down to the monolayer? Let's find out. For silicon, this is the case. We have around 150 watt per meter per Kelvin. The thermal conductivity starts decreasing as we decrease the thickness, and we have more than a factor 10 lower thermal conductivity already for a 10 nanometer film. And what was known when we started our research, we had this available literature, and I'm only showing here experimental thermal conductivity values measured, all of them with a Raman thermometer. So it was clear that the thermal conductivity decreases while making them thinner, but it was not clear what would happen at the monolayer thickness or what would happen with the thickness in all the very thin regime. So how can we explore this range? Well, we will use our thickness control suspended flakes to perform Raman thermometry experiments. And how does this work? This is based on Raman spectroscopy. And basically, Raman spectroscopy is the inelastic scattering of light by optical phonons. We resolve this frequency shift from our laser to our inelastically scattered light thanks to a spectrometer. And basically, we find peaks like this spaced by a Raman shift. So, Raman thermometry. The first thing we need to know is to characterize how our observable shifts with temperature. So basically, we take our suspended region, we shine very low laser power. This is to avoid laser-induced heating effects. And we find out how much shift we produce by a given temperature increase in the sample. This, what we're looking here, is the frequency of this A1G out-of-plane atomic vibration, which is carrying little heat in our samples. In the second experiment, what we do is to perform laser heating at room temperature. So basically, as we increase the laser power, we have a similar Raman shift. This is a red shifting of our observable just by increasing the laser power, meaning our laser is hitting the sample, and therefore we can correlate the given shift at a given power with a given temperature increase in the sample. And so we have an optical thermometer. So let's plot the temperature increase at the center of our suspended region as a function of laser absorbed power. We see that our thinner samples are on the left side, while our thicker samples are on the right side. So they are very well sorted by thickness. This is a very intuitive result. A thicker material needs a higher absorbed power to increase the temperature to the same level as a thinner material. This is basically because we have a larger volume in which heat spreads, and therefore we need more power to heat it up to the same temperature. And how this relates to the thermal conductivity? Well, we only need to know the thickness of our flake, the radius of our hole size of our suspended region, and the radius of our laser spot size. We can now plot the in-plane thermal conductivity of these flakes, and we see that not much is happening with thickness, but it seems that it's going slightly up for thicker flakes. In any case, all our flakes are extremely thin, and importantly, down to the monolayer limit. So, to understand our results, we ask our collaborator Roberta to perform ab initio simulations using the Siesta package, and we see that our experimental results agree very well with the calculated thermal conductivity. But importantly, we understood that things were actually changing. For thick materials, the main contribution to the thermal conductivity comes from modes centered around 1 terahertz. If we decrease this in the thickness, we have the contribution from these phonons decreasing, and the appearance of lower frequency phonons for the mono and bilayer samples. These low frequency phonons have in turn very long mean free path, and therefore they travel very far away before they start scattering. So how does this compare with literature? Well, we really filled the gap. So back to the case of silicon, this is as if our 2D materials that importantly we can thin down to sub-nanometer thickness maintain their thermal properties down to the monolayer. We summarized our results in the Journal of Advanced Materials in 2022, this very nice paper where we also discuss the effects of the environment and potential experimental artifacts that can occur in this type of measurements. So let's move on to the last and biggest section of my talk. Here we want to study the out-of-plane heat transport in molybdenum disulfide by using time-domain thermoreflectance. So as we've said, we will use plates supported on a substrate, which is our heat sink, and we will use a metal transducer, which is what will give us our observable. The change in reflectivity of this metal will tell us how much the temperature has increased at the surface, and therefore we can relate it with the thermal properties of our material. Importantly, we studied the possibility of coherent heat transport in a single TMD, which has never been done before. So what is this coherent heat transport and how do we harness it? In 3D materials, this can be done by using periodic three-dimensional superlattices. This is two three-dimensional materials grown on top of each other in a periodic fashion. And this means that you are creating multiple interfaces, which in turn gives a reflection of all these propagating phonons at each of the interfaces. And the reflected phonons can be in phase or not in phase. If they would be in phase, they would constructively interfere in the backwards direction, meaning that no propagation can occur through our material. If the waves are not in phase, propagation can occur and our wave is transmitted. So there are many experimental works that show this kind of trend and show a crossover from incoherent to coherent heat transport as we increase the interface density. This is, we decrease the period thickness. We make these constituent materials thinner and thinner, and in turn, when they are very thin, so high interface density, phonon transport is coherent. When they are thicker, we have a particle-like behavior and phonons mainly scatter at the interfaces. So how could we harness coherent phonon heat using 2D materials? Well, we could make 2D material superlattices. So we can stack two different 2D materials in a periodic fashion, and therefore we should be able to observe the same effects. However, this is challenging. The fabrication of these samples is not straightforward, and there are only two experimental works which studied the possibility of coherent heat transport in two-dimensional superlattices. However, none of these works provided a clear evidence of coherent transport at the nanoscale. In any case, a theory work appeared where they study graphene HBN superlattices, and they demonstrated a similar crossover from incoherent to coherent transport. But wait, isn't a 2D material already a periodic structure? It seems so. This is made of layers and van der Waals gaps. When we change the thickness, the dispersion relations change, not introduce more resistant channels. And these materials have the highest interface density available in the realm of material science. So these materials would fall on the extreme end of this graph, implying that phonon heat should behave as waves. So let's perform time-domain thermoreflectance measurements on our flakes. Our flakes are on a substrate and they have this metal transducer on top. We now use pulsed lasers and we modulate the excitation laser. This is the laser that introduces heat in the system. And we use a time-delayed probe laser, also pulsed, the reflectivity of which contains information at the modulation frequency of the pump beam. This is, we are detecting reflectivity changes that occur given the presence of the pump beam. And how does this look like? Look in at the signal that we produce by a locking amplifier, we have our pump introducing heat in the system, the heat decays, and we probe this decay at varying time delays between the pump and the pulse. And how does this look like in our lab? Well, we have a fundamental laser that emits laser pulses centered at 1030 nanometers. We split this laser in two lines, and we use a second harmonic crystal to frequency double our probe beam, so we make it green. The pump laser goes through an electro-optic modulator, and we produce a sinusoidal modulation of its amplitude in the frequency between 1 and 10 megahertz. This beam goes over a mechanical delay line, which introduces our control time delay between pump and probe. Both of these beams recombine at an objective which focuses the light on the surface of our metal transducer. The reflected light, we take it into a silicon photodiode, and we demodulate the signal using a locking amplifier. We also have a white light imaging system to visualize our sample and to know where are we performing our experiments. In the lab, it looks like this. It is very complicated, but mainly you see the two laser lines recombining and eventually going into our objective, which focuses onto our sample. And our sample is here inside the cryostat, which allows us to control the temperature. The reflected light is guided to our detector. So let's perform our time domain thermoreflectance experiments or on our thickness control supported flakes. So for the thick regions of our flakes, these are 160 nanometer thick flakes, we have our pump laser introducing heat in the system and the heat decaying. If we use a smaller laser spot size, the temperature increases much more, and therefore it produces a larger signal. These thick flakes we model using the anisotropic model, considering heat transport in the out-of-plane direction and in the in-plane direction. This is because they are thick, and heat transport occurs both out-of-plane and in-plane until eventually it heat sinks on our substrate. With this, we obtain values for the interfacial conductance between our transducer and 2D material of 34 watt per meter square Kelvin and thermal conductivity of around 2 watt per meter per Kelvin. These are values in agreement with the literature, which we will see very soon. Let's first convert these results into an effective total resistance, so a thermal resistance provided by transport across the interface flake and the interface towards the substrate. So how do they compare with literature? For the thick flakes, we get pretty good agreement with the available literature values, and basically the difference between our experiments with these available experiments is the use of a different transducer material. They use aluminum and we are using gold, and still we get similar numbers. For the very thin flakes, now it is not so relevant the heat transport within the flake. It is all dominated by the interfacial resistance conductance between our transducer and our substrate. In any case, our flakes agree very well with available literature. They are very close to the ballistic limit. The offset is the effect of the interfaces. And the difference between our results and these experiments is that they used a sister technique to do these measurements. These are frequency domain thermoreflectance measurements. So using continuous wave lasers and resolving in the modulation frequency of our pump, instead of using pulsed laser systems and looking at it with time resolution. And what happens for the flakes with intermediate flake thickness, we also model them as just an interface, and we obtain an increased interfacial thermal resistance. how does this compare with available literature? Well, here it is only covered by these results by 𝐒𝐭𝐮 et al., where they study randomly oriented molybdenum disulfide. This means their materials are polycrystalline, and therefore the stacking between the different layers is random. So they should be more resistive than expected. However, our flakes show an even higher thermal resistance. So could it be that coherent phonon effects are present in our experiment? Well, I also didn't show you the data for 3 layers and 10 layer regions. And the reason is that these regions show barely no thermoreflectance signal. So we cannot apply our diffusive model to describe these specific regions. So we hypothesize that at specific thickness regions, coherent phonons reflect at the different interfaces and destructively interfere in the backward direction, therefore enhancing our transmission into the substrate. To understand this, we performed several imaging techniques. First of all, our optical images of the flake before we deposited our transducer material. They show a nice optical contrast for the different layers, but once we deposit our metal transducer, now we're covering them with metal, we cannot distinguish the different layers of the flakes, but we do see an increase in reflectivity of our probe beam as we increase the thickness of the material. And this is because we're using a quite thin transducer layer. If we perform time domain thermoreflectance imaging, first of all, to our surprise, we have single layer resolution. So we can specifically distinguish the different layers in our sample. Second, we see a sign change in the thermoreflectance signal for flakes between 4 and 9 to 10 layer thickness. And third, there are regions that show barely no signal. If we plot the intensity profiles of the reflectivity and of the thermoreflectance along the same line in our sample, we see a monotonous increase in reflectivity and a sign changing eventually 0 at 3 layers and recovering sign for thicker films. If we plot the signal magnitude normalized to the substrate value for all our measurements, these are averages of multiple measurements and samples, so that we can cover the entire thickness range, we see this oscillatory behavior. And this is an experiment that is analogous to an optical 𝗗𝗿 cavity. But in this case, we're using phonon heat as our observable. And these specific resonances, where we see no signal, would correspond to 1/4 and 3/4 wavelengths of the phonons that carry heat. So let's perform time domain, temperature-dependent time domain thermoreflectance experiments. We've seen that at room temperature, our 3-layer region shows barely no signal, and this effect also happens for around 10 layers. And when we decrease the temperature down to around 120 Kelvin, the region that shows no signal is not the 3 layers anymore. Now it is a thicker layer. Specifically, 5-layer molybdenum disulfide shows near 0 signal at low temperatures. Our intuition says that decreasing the temperature should increase the phonon wavelength, and therefore these resonance conditions should be satisfied on a thicker material region. So let's compare our 2 experiments. At room temperature, we had this oscillation with our minimum around 2 nanometers, so 3 layers. At lower temperature, this is shifted and the minimum signal is now at 5 layers. But Could there be an alternative explanation? Well, as our transducer is so thin, it is possible that we have optical effects playing a role as we change the thickness of our material. And to understand this, we performed transfer matrix method simulations, considering all the materials in our sample with their thicknesses and their optical properties. With this, we can reproduce an increase in reflectivity towards thicker flakes and a sign-changing thermoreflectance signal that crosses zero in between 3 and 4 layers and at around 10 layers, similar to what we observed in our experiments. So to recap, we've seen that our TDTR measurements at room temperature show good agreement with our thick and atomically thin flakes. We show that we obtain a larger than expected thermal resistance for the intermediate flake thickness. And using TDTR imaging, we obtained single layer resolution of our buried molybdenum disulfide flakes. We showed a sign-changing signal between flakes for flakes between 4 and 9 layers, and we show near zero TDTR signals at specific thickness regions of 3 layers and around 10 layers. We confirmed with temperature-dependent time-domain thermoreflectance measurements that specific thickness-temperature combinations would lead you to a control of the thermoreflectance coefficient. So you can either change the thickness or change the temperature to achieve zero thermoreflectance signal wherever you want in your sample. So we explained our results in terms of potential coherent photon heat transport and in terms of coherent photon effects. So this brings me to the summary of my talk. In section 2, we've seen that using a home-built dry transfer setup, we can fabricate both supported and suspended samples of TMDs. Actually, this could be any material, and our methods would still apply. And we've used our suspended TMD flakes for the first optical absorption measurements as a function of crystal layer thickness. In the third section, we've exploited our suspended molybdenum diselenide flakes for in-plane heat transport experiments, and we've seen how our results filled the gap in the literature. In the last part, we've used our supported molybdenum diselenide flakes. We've performed time-domain thermoreflectance and obtained the total thermal resistance for many flakes with many thicknesses, agreeing in the thin and in the thick part, and showing strange behaviors for intermediate flake thickness, which we tried to explain using coherent photon heat and coherent photon effects. Actually, to unravel these two potential contributions, we are performing cross-sectional transition electron microscopy measurements to look at the quality of our interfaces, and also we are performing probe wavelength dependent TDTR measurements, which would allow us to observe whether it's coherent photon effects what we're seeing. So I didn't have time to tell you that we started with an empty lab in 2019. So we did everything from scratch. We've built a lab. It took quite several years. We've dismantled it. We've packed it into boxes. We've loaded it into a truck, and we've built it again. So research is not done alone. And I would like to thank specifically my supervisor, Klaas-Jan 𝗗𝗗𝗗. I would like to thank Sevin, my PhD colleague, Alex, who is there in the audience as well, Jake, might be online, Bohai, Nupur, Ronnie, and Ant, and many more that I'm missing here. I would like to thank the people at TUE, also from Klaas' group, in particular Loic and 𝐸𝐭𝐿, who are also here, and of course Eric, Josh, and Henny Manders, who made our stay in Eindhoven much more pleasant. I would also like to thank all our collaborators, the people in 𝐸𝐭𝐿 group, especially 𝐒𝐭𝐻𝐻𝐿. I would like to mention Pablo 𝐒𝐻𝐿 and 𝗗𝗶𝗿𝗲𝗰𝘁, Matthew, Zeyla, and Oli, who performed theory for us. I would like to thank Gustavo Ceballos, Rafa León, the maintenance team, and also Raúl in the nanofabrication facility. And I would like to mention Bart, who I hope is online as well, 𝗗𝗶𝗿𝗲𝗰𝘁cie and Kai, who helped us understand our thermoreflectance measurements, Miguel Muñoz and Elvira, and of course, the thesis committee. Andrés and Maria José, also Eric, thank you very much also for reading my thesis. It was maybe dense. And of course, thank you all for coming to be here in this special day.
Yeah, thank you. So we have finished the presentation part of the defense. So we will move on now to the actual questioning and answer, right?
Sure.
So we will start with Professor Maria José Esplandiu. Okay.
Yeah, thank you very much, for your very clear, well-organized, presentation. It has been very, very good, and it has helped to understand many things in a simple way. But before going to the questions, I want to comment a little bit on you and on what I have read, in the manuscript. And then we can go to proceed to the questions. So for me, it's a big pleasure to be in this tribunal. Perhaps nobody knows, but I know you since you were a student, undergraduate student in the first year of the degree of nanoscience and nanotechnology, and I was teaching there. And I can remember you very well in this time, since you stood out like as a bright and committed student among top 5% of the students that I had. So I was very happy to have you in my class. And also today, I'm really delighted that to be here and see how you have evolved into such outstanding scientific maturity that I can see from reading this manuscript. So in this thesis, you have addressed a topic that is very rich in physical content, but also is very challenging, very complex. Nevertheless, you have overcome all this, and have got very high quality production output, very relevant achievements, and also I was very impressed with the publications, all the productivity in your contributions as papers. So here is only a small, very small part, very small part of what you have done. So I have counted that you have more or less like 15 papers already published, and 5 that are under revision, if I'm not, or under preparation. So it's a very impressive production. So you have approached this topic with outstanding methodology, contributing for the setup of the very sophisticated techniques, programming, modeling, analyzing data with care and rigor. So all these things in the thesis clearly shows that you have a rich, a deep technical and conceptual mastery. So is what I see from this reading this manuscript. The other thing, okay, the manuscript is very well written. Yeah, so it has been okay. There was a part that it was tough for me, but it's because it's not easy, no? Yeah, all the development of the theory and of the techniques, and I was trying to do analogy with impedance spectroscopy to understand a little bit, but it's not so easy. But nevertheless, yeah, you have written. Yeah, it was very clear, well organized. Yeah, with a logical flow. Yeah, from the introduction, the theoretical background, the results and conclusions. Yeah, so at this point, yeah, although I have not gone to the questions, I want already to congratulate you for this outstanding piece of work, and also congratulate you for the guidance. I can see that you have both profited from yourself, no? Yeah, and so the guidance of with the knowledge of class, and also transmitting good practices, yeah, for being a rigorous researcher. Okay, yeah.
Thank you very much for your kind.
So now I will go to a little bit the questions. I have many, but I won't do that always. Yeah. So, yeah, I only want to ask you some questions that are coming from my curiosity. I should say that I'm not a specialist in this part in thermal management, and you know, I only know a part of the 2D materials, but in applications that are more in the chemistry. But okay, so. A central point in your thesis are all this is the setup of technique for assessing the heat transport of photons. So the first thing that I would like you to comment is that you have in the manuscript you have addressed the advantages of the time domain thermal reflectance techniques. As an ultra-fast technique, but I would like to know a little bit the limitations of this technique for the topic. You can comment a little bit some limitations of this technique.
Well, thank you very much for your kind words.
You're welcome. Yeah, be said.
I must say that time domain thermoreflectance is a very complicated technique. It's not easy to implement, not easy to perform with confidence, let's say. It's not that you get data and directly can observe that something special is going on. You need to perform rigorous analysis, and the thermal model to describe these experiments is very complicated. It has so many parameters that can influence your outcome and so your results that you need to take very good care of, first of all, reducing the unknown parameters. Second, all those parameters that you're fixing, they need to be quite accurate. And therefore, it is very, very tricky. Here, we take advantage of our thin transducer to have the possibility to see our flakes underneath the transducer. If we would use aluminum or a metal with higher electron photon coupling and thicker transducer, as is typically used in this kind of experiments, this studying the thickness dependence, it's much more complicated. So we have here a trade-off of being able to study how things change with thickness, but still, being able to show heat transport. Here, it is much more complicated than this. Our transducer is thin. There are hot electrons that eventually reach the interface before the heat is thermalized. So probably we are not introducing the heat strictly at the top surface of our transducer, and therefore it's not that the thermal model perfectly describes our heating conditions. So it is a very complicated technique, and you can take very good care of some things or some other things, but having good set of experiments that can allow us to see these observations would be tremendously complicated.
Yeah. And just in this direction, so because you have focused on the out of plane thermal conductivity, but you don't have so much sensitivity in the in plane, no? But can you calculate something or in plane?
Yeah, of course.
And how compares with the, for instance, the the Raman thermometry, for instance?
I mean, we're using very thin flakes. Our thickest flake is 160 nanometers. So, I mean, we can definitely estimate the sensitivity of every parameter in our model. The problem is that also adjusting a different parameter will affect the sensitivity that you retrieve for a certain parameter. So I would say that just because we use spot sizes in the micron range, we are effectively decreasing the effects of in-plane heat transport. Our laser spot is this big and our material is this thin. So we are homogeneously heating, let's say, a large area of our transducer, and therefore the in-plane heat would play much smaller role than the out-of-plane heat. So we can show this with sensitivity analysis, which you may find in the appendixes of my thesis. And the Raman thermometry, of course, you can also measure bulk materials, out-of-plane conductance, interfacial resistances, and so on. Here we focused on suspended films, so trying to perform the same set of measurements and out-of-plane properties using Raman thermometry would be slightly more complicated. Also because if you don't have a metal transducer on your sample, you might be hitting quite a slab of your 2D material, or all of it if it's very thin. So studying the out-of-plane thermal transport properties is limited to bulk samples for Raman thermometry, I would say.
In the use of gold with a titanium additional layer, so the choice of gold was because of the laser that you were using, the fact that you could extract the from the other laser the other component, no? So
yes,
and so would you have other results if using another wavelength, for instance, for aluminum, or
yeah, the relevant.
How was the choose? I don't know, so much about that. If you can comment on that, why you were using for probing the 532 and not. I don't know if there's an issue there. If you can get.
Yeah, of course, this is very relevant here. First of all, our setup was limited to these two wavelengths. We have fundamental laser centered at 1030, and we can produce the frequency doubling. So half the wavelength, 515 nanometers, which is green. If we look at the available metal transducers used in the literature, we can see that most experimental studies are using their probe at 800 nanometers. This is the wavelength of titanium sapphire laser, and therefore it's very common, and so it is available in several labs. So the typical choice is aluminum. Also, aluminum has a large electron photon coupling, and so heat thermalizes very quickly. But in our laser, we have a wavelength of 1030 and 515, so which we use as pump or probe. First, we started using aluminum and using 1030 as our probe wavelength. It's the obvious choice. Also, the pump would be 515, it would have higher energy, so it all makes sense. But we were having significant difficulties in finding where are the layers, how can we measure different layers. We will need to prepare so many samples if we want to cover all this thickness range. So eventually, we decided to switch to gold. Gold has these two peaks of thermoreflectance where you can get a much higher signal using green or blue wavelengths. So the reflectivity changes much more for the temperature increase. So in this case, as we are limited to these two wavelengths, we decided let's switch it around. Let's use the green as our probe and the infrared as our pump. Of course, we started getting much better signal, and like a miracle, we started resolving all these thicknesses of our flakes with some trade-offs, of course. But yeah, this was the
main, yeah.
the reasoning behind.
But because you also mentioned that you can have some interference with the titanium. I don't know if you can use without the additional layer.
I mean, eventually it would be better not to use titanium,
Yeah.
because it has been shown titanium can react with
And aluminium also.
And aluminium also. This I didn't know.
Aluminium is very reactive one, yeah.
This I didn't
very
know.
reactive one. But that's why I was just wondering what happened if you do without, yeah.
I think the point would be, first of all, that on the bare substrate, you would have a worse coupling between gold and silicon oxide, and therefore lower transport towards your substrate. So probably this would also imply less sensitivity to heat transport across your flake. But yeah, we never explored experimentally what happens if we do this thickness dependence without the titanium additional layer.
Okay. So sometimes I have I don't know the interpretation of the V in and the V the ratio. So how to easy have a general trend. When you say fast decay, that means that or slow decay. Slow decays, that means that the heat flow is the thermal conductance is higher. It's difficult for me to visualize.
It is not very easy.
Not very easy.
This is a very relevant point, because the lock-in amplifier spits out these two signals, the in-phase signal and the out-of-phase signal. The in-phase signal, in principle, is more dominated by the pulse heat diffusion. So the pulse heats up the sample, diffuses, and the out-of-plane signal is a result of the modulated heating. So we are performing heating in a sinusoidal fashion, but it's pulsed. So the heat increases, decays, increases, decays, and eventually this modulation leads to a delayed thermal response, which is what we measure in the out-of-plane, the out-of-phase signal. But both of these signals are influenced by the optical properties of the film, the reflectivity and so on, and therefore our thought that we could have coherent photon effects. But the ratio of the two signals is not anymore affected by the optical properties, because they have the same dependencies and you divide one another. So you remove this contribution, and therefore your signal mainly decays as a result of heat transport properties. So obviously it also depends on the modulation frequency, the laser spot size that you use, the heating conditions that you are applying.
But you cannot, for instance, there in this image, in this figure, to say how if you have to compare 2 point, if that is the spot size. How should be in this spot size, and in the other, you can say in the 2.4 the thermal transport is higher, or
it's not that it's higher. The sample has its own thermal conductivity in the in-plane and out-of-plane directions. The point here is, let's say, a higher temperature and a faster decay would imply a more efficient heat transport.
The fast decay more efficient. Okay.
You are increasing the temperature and you are quickly dissipating this thermal energy from the hot spot. So the difference between the hot and the cold is now larger, so larger signal,
Yeah.
and the faster it decays, the faster.
Because the cumulative heat, when you have a.
Exactly. Eventually, if you start having a more resistive behavior, the curve flattens, and eventually the signal will also lower. You start overheating the material, and therefore your contrast between the on and off heating is lower.
Perfect. Perfect. When you so you mentioned about the green oscillations in silicon oxide. Yeah, how can affect this? Yes, you can go because obviously depending on the modulated frequency, you can go deeper or how you can how they can interfere this green oscillation from silicon oxide.
Yeah, thank you very much for this question because it's something I didn't have time to show. Basically, there are two explanations or two potential explanations for these oscillations. One would be Brillouin oscillations, and the other would be resonant acoustic phonons. We actually discarded that this is Brillouin oscillations, which would imply the probe beam leaking into our transducer and interacting with the acoustic phonons of the dielectric material underneath. This we confirmed with other set of experiments, which I also didn't show, that are resonant acoustic phonons in our gold film. So we are launching phonons that start resonating because of the wavelength and thickness in these materials. So basically, we observe this as this kind of oscillations, and these have massive implications in what we eventually find. We have for the bare substrate these oscillations, but for a 3-layer, these oscillations are supported for way longer. So basically, our 2D material is decoupling the transducer from the substrate just because of these weak van der Waals interactions.
Okay, just moving to the coherence effects of phonons. So you were comparing and doing the analogy of a fabric pellet, yeah, and so there, are you taking a distribution of phonons modes, yeah, or to reproduce the? Yeah, can you comment on that?
This is a very good question because, of course, here retrieve one single wavelength for all these samples. Of course, the wavelength may change with thickness. And of course, heat transport is a broadband process. There are many phonons contributing to this. So this would be an averaged phonon wavelength, let's say.
Okay. So you say that there was a theoretical work talking about a coherent and for 2D materials, there are some works on this coherent. I don't know, yes, but it was with the heterostructures, no? But for this molybdenum disulfide, there are no other reports on that, no?
Molybdenum disulfide is considered here. They perform stacks of graphene and molybdenum disulfide, but
not as
it's not a super lattice in the sense that it is not periodic. Of course, it's periodic, but the thickest sample they studied is 5-layer thick. Graphene, molybdenum disulfide, graphene, molybdenum disulfide, graphene. So eventually a super lattice would be something periodic and repetitive or a longer scale. The point is that here they do thermal engineering by stacking these alternating layers of materials with high contrast in their mechanical properties and phonon properties. They achieve a thermal insulation which is much higher than a single of each of these materials of the same thickness than this heterostructure. Still, there is no coherent phonon heat evidence in these experiments But to my feeling, it's just because the material is so thin that you cannot have interference effects. Like the phonon wavelength is probably still larger than their thicker material.
No, I was very impressed, yeah, with the studies that you did, yeah, that you can find at certain layers anomalies, yeah. And but you have the other problem that could be optical interferences, but the study as a function of temperature and looking at the phonon wavelength cannot discard the optical artifacts, or
It is not 100% conclusive.
it's not.
We would like to, but
Mhm.
it's what it is. We need to consider other possibilities, and even if it can provide a plausible explanation, it doesn't necessarily mean that we have coherent phonon heat transport. So it's a hint that something is not behaving
Not
as well
behaving,
as how we expected,
Mhm.
but it's not definite proof that we have coherent heat transport in these materials.
Mhm. And so you were mentioning some steps to analyze better. Yeah, can you comment a little bit more on that, or
What do you mean?
to try to discriminate? Yeah, if you have more optical interferences or phonon interferences there.
Yes, basically we are currently performing probe wavelength dependent TTR, and this relates back to the thermoreflectance coefficient of gold. Basically, let's say we are probing here and the effect of 2D materials would produce maybe a shift on this resonance. It would be possible that this point with 0 thermoreflectance coefficient comes at our probe wavelength. So we are trying to perform measurements at different wavelengths here, and the idea is to see what changes, or if we can find the same results, or if it's all just consistent and heat can propagate coherently.
Okay, thank you. So I don't know how much that, yeah, it's just only, can I ask one question about Raman thermometry? Yeah, it's very fast. Yeah, it's very fascinating. Yeah, I think that I have so many curiosity, but I want to ask something about Raman. Because I have seen people that they try to do Raman thermometry, by using a stimulator laser that can produce heat, and another that is for probing. So can you comment what you the advantages of using this technique with respect to this, and also with the time result Raman?
Yeah. Thank you very much for this question, because this I didn't even have the chance to show it in my thesis. We did perform 2 laser Raman thermometry. We used the second laser to heat up our materials, and we performed maps of how this Raman shift changes with temperature. You can retrieve the entire temperature profile in your films, which would make it potentially contain more information about heat transport in these materials. However, the setup was not ours, so we had very limited time on the setup. Performing this kind of measurements is much more complicated technically. You need to align the 2 lasers, you need to have very good control, and measuring different samples have the same conditions. But if we only had little time allocated now and then, it is very difficult for us to come back to the system and find it as we left it. So this was introducing much more statistical deviations in our measurements, and we decided to go for the simple 1 laser Raman thermometry method, which works equally well. So this was the main reason. But yeah, it could be advantages, because in this case, your probe laser is not hitting the sample, so you are just recovering this temperature profile.
And with respect to the other, because you are looking to the red shift of the peaks, but also you can look at the different of intensity of the anti-Stoke and Stoke signals. Yeah, I don't know if the people in this context is a technique that is also widely used. Yeah, based on the intensities, or you have more problems, or if you can comment a little bit on that. Yeah.
Yes, of course, there are many ways to estimate the temperature from Raman measurements. However, this setup, the setup of 𝐒𝐿 back in the days, was optimized to measure shifts. It had very high resolution on the frequency of this mode and not so much on the intensity of this mode. Also, if you want to look at the intensity ratios of the stocks and anti-stocks, which is related to the fallen population and so to the temperature, you need to have less resolution as well. You need to look at a wider window. So this setup is precisely designed to measure shifts. Now, in the time-resolved Raman thermometry setup that we also developed complementary to our probe setup, is that we can only look at the intensity difference between these peaks, and we have less sensitivity to the shifts. First of all, because our lasers are pulsed, and second, because we don't have that much frequency resolution as they have in this big spectrometer. So yeah, in our case, we would look at intensity ratios, but in that setup, the most obvious thing to do is to look at shifts of the Raman signal.
Thank you. I don't want to get more in time. I have a lot of questions, but I don't want to, because it's a very rich thesis, I should say, and but I have to give time to my colleagues. Yeah, I cannot take all the time for everything. So thank you so much, and congratulate you, for this fantastic work.
Thank you. I think it's now turn for Professor Prof to give his exactly. So if you could please up there, exactly.
Eric, are you there?
I am here.
We cannot see you.
No.
Now you see me very large.
Yes. Yes.
Sorry about that.
You look good.
I brought my my Stanford mug with me, just in case, to wake me up. Thank you very much. How much time do I have, by the way, roughly?
20 minutes.
Okay. I think I need less than that. Thank you very much. This was very nice. I took some notes, and I just want to say that the presentation, the slides, the graphics, the text were excellent. I emphasize these things to my students a lot, and I think I will use your presentation as a good example for how to have the right balance of text and graphics and the right bold and colors and all that. So I thought that was very, very clear. So that's great. In terms of technical questions, I actually don't have too many because I read your thesis pretty carefully, and I sent you some comments. And so maybe during your talk, I wrote down a few things by slide number. So maybe if you could go, let's just go in order. If you could go to slide number 17. I have.
Sorry, 1 second, Eric. Maybe you can minimize a little bit the window so you can see both the presentation and.
How do I do it?
Yeah, or well, if I turn off my video, probably same thing.
Like that. It's great.
It's working?
Yes.
So, sorry, can you repeat?
So go to slide number 17, if you don't mind.
I cannot see the number.
To the bottom left, right?
Yeah, but we have an icon.
If you type 17 and enter, you will go directly to it.
Really?
Yeah.
No.
No?
You count from the video. 1, 2, 3.
Yeah, that would be better.
Because it's a PDF, sorry.
Yeah.
I thought it was a PowerPoint.
Slide number 17.
Yes.
Yes.
So I was, I was trying to understand this. This is the circle here is suspended, right?
Yes.
Okay. So you basically found that if you heat it up on a hot plate, the transferred film becomes smooth,
Yes.
right? So two questions about this. One is when you heat it up, is it in air or is it in a glove box, or what's around it?
It's air.
Okay. And does the material degrade if you heat it up in air at 150 Celsius for 30 minutes?
That we don't know, but as if it stays suspended, I believe the crystal is undamaged. But of
I
course,
see.
we can compare before heating, after heating, if the material changes.
So because so which material is this for all your TMDs or just for molyselenide?
I mean, we prepared suspended samples of other materials, but not specifically me. And these wrinkles don't occur in every transfer. So
I see.
cannot tell you if it's material specific. I mean, I can tell you that not always it works. So
Yeah, no, I understand that part. But the reason I ask is because I know the selenides tend to be more sensitive to air than the sulfides. So if this was molyselenide or tungsten selenide and you heat it up in air, I'm just wondering if you slightly oxidized it.
to be honest, I don't know if it oxidizes, but if it does, it probably oxidizes from the very first instant that we prepare it, because we don't see any change in their properties with time. We have this kind of materials suspended for many years. Even monolayers of these materials remain suspended for years. I would say if there is a bit of a degrade of the crystal structure, these materials would collapse. They are very fragile, very thin, and so they break.
Well, they wouldn't collapse necessarily. I'm just imagining that the selenium atoms would get replaced with oxygen atoms eventually. So you're starting to get, instead of molyselenide, you get some molyoxyselenide or something like that. And because we've seen these sorts of changes in California air, and I I'm just trying to think if we have different air here. But especially the selenides, we know that they degrade pretty, they degrade more readily than the sulfides. And some of these changes are picked up by Raman, and some of these changes are not picked up by Raman, but they're picked up electrically. So we know, for example, that the electrical quality of our selenides degrades within days if we don't encapsulate them.
Yes, it is possible that this occurs, but would it affect, for example, the photoluminescence? Because our suspended samples, especially the mono and bilayers, they show photoluminescence emission where we expect it, even if they are 1 or 2 years old,
Okay. I mean, they probably would affect the photoluminescence, but I cannot tell you by how much. And so unless you did a careful time-dependent study of the photoluminescence, I think it would be difficult to tell. But you're basically saying that, in your experience, monolayer MOSE2 photoluminescence does not change with time when it's suspended.
Not at all.
Yeah.
We haven't seen any dramatic effect.
Okay. So I'm not the person doing these experiments. I'm relying obviously on what my students and postdocs tell me. But my impression was that our selenides, the photoluminescence and the Raman do change over time. And now, interestingly, we don't look at suspended samples. We look at samples on substrate. Almost always. So, that could mean multiple things, but I would think that suspended samples would be maybe even more sensitive because the atmosphere can go both from the top and the bottom to attack them, you know. And anyway, you know, I was just sort of curious about this. We should probably compare notes in more detail offline. But it's something that I wanted to, you know, that was on my mind as soon as I saw this. And by the way, especially at, you know, if you bake it at 150 Celsius, all these things would be accelerated at 150 Celsius, right? All the sort of reactions and it wouldn't collapse. It would just, you know, you just replace a certain percentage of selenium atoms with oxygen atoms. You may not even be creating vacancies necessarily. And for sure, the material gets covered in some sort of hydrocarbons if it's left out in air. So any material will get covered in very, very hard to remove hydrocarbons and water, but the water can be removed. The hydrocarbons, not so much. So, you know, again, I think electrically we're sensitive to these things. I don't know, you know, thermally if we are or you are. I don't know. I'm just, you know, thinking out loud. Okay.
Yes, I think it's a very good point, and I don't have an answer with results that support it, but
yeah,
I would expect that if this oxidation has occurred, it has occurred before we perform the actual measurements, because we left the samples in air, we put them in and out of the desiccator for several characterizations. So eventually, we never made a flake and measured it 5 minutes after we prepared it. So
yeah.
I could imagine that if it would have a strong effect, our flakes would also show a much different trend, because not all of them were heated to flatten again, let's say. So only we found wrinkles. We did use this thermal annealing, and so we flattened flakes. So we don't see this dependency, which flakes were heated and produce a change in our observable. We didn't notice this.
Yeah. Okay. I mean, just something to, you know, something to look into and to compare notes on. Go to the next slide, number 18. Actually, maybe I'll use my. Can you hear me okay, by the way?
Yes.
Now it's okay? Okay. I could also use my headphones, but if you hear me without them, then I'll stay without them. So when I was looking at this sort of a picture and maybe a few others you showed later, I was thinking about the roughness, the surface roughness of these samples. Have you tried to quantify the surface roughness with an AFM of these suspended films versus the ones on substrate?
Yes, thanks for this question, because I didn't have time to show it. So yes, indeed, we performed AFM both in supported and suspended regions, and we observe sub-nanometer roughness in the suspended regions and 1 to 2 nanometer roughness for the supported regions.
Okay, very nice.
Supported on gold, so it forms these blisters, which we avoid in our measurements, but still it conforms very well with the roughness on the supported part.
I see. So the edges of the hole are actually covered in gold. That's gold right there. It's not SiO2 or something.
Yes, it is a silicon nitride membrane that we first gold coat, and then we transfer our material on top. So the gold provides this stickiness to the TMDs that helps the release of these very large suspended areas. So you can see that the flake actually conforms on the surface. Here there is 120 or 30 nanometers of, it's not sagging, but it conforms on the walls, and then you have the suspended area.
Right, but the yellow part that says supported, that part is gold, correct?
Yes.
Okay, all right. And so there it's just picking up the roughness of the gold. It's nothing specific to the 2D material. It's the gold is what's rough, correct?
You're right.
Okay, all right. Okay. Is this image published, by the way?
Yes. This image is probably in the fabrication and characterization
Yes.
paper. Yes.
I see. I might email you later to get some more quantitative numbers for this because we're interested in the roughness of suspended films, in our case, compared to films on SiO2. So that's what we need that number for something, for a calculation. I think related to this, if you could go to slide number 38. Yeah, so related to this, and maybe you said this and I missed it, but did you quantify the G, the thermal boundary conductance, with the SiO2?
We actually fixed it to the value you reported previously. Well, actually, we've tried to also extract it, but eventually you need to perform more measurements in more configurations to be able to extract all these unknown parameters. In this case, we are already extracting 2 parameters.
Yeah.
Top interface and the thermal conductivity. And we are using 2 different spot sizes and 2 different modulation frequencies. So yes, we could have changed also the interfacial conductance, but we saw that we have way less sensitivity to the second interface compared to the first interface, and therefore fixed it to the value that people typically use from 14 to 20. Then we use 18 watt per meter square Kelvin.
Yeah, I see. Yeah, okay. Well, I'm flattered that you found our value useful. But you know, we are never quite sure what value to use either. So I always tell my students to just use a range. So yeah, 14 to 20 sounds like a good range. But yeah, because the reason I asked this is so my follow-up question would have been, if you studied how this interfacial thermal conductance is, if it's sensitive to some sort of surface roughness. And, you know, it sounds like you didn't study the one for SiO2, but can you comment on any other Gs that you extracted?
Yes, it probably could depend on surface roughness, although exploring that could be extremely challenging. No? You should make samples with different surface roughness and then test how the interface depends on that.
Yeah.
Not knowing if your flake is the same on the 2 samples, right? It's actually a different sample.
Yeah,
so
yeah.
It would be
I agree.
What I can say is that silicon oxide in typical silicon oxide silicon wafers is atomically flat. It has roughness of 0.2 or 3 nanometers, which means less than the thickness of a single layer of our material. So we can consider it atomically flat. Therefore, we put our 2D material on top, and you can see it is also very flat. You don't see blisters, you don't see spots or dust or whatever. Our TTR maps also show super homogeneous thickness regions, implying that our interfaces are very conformal to a flat surface. Then growing the gold on top, it's like growing gold on a flat surface. Of course, it could be different how it grows on molybdenum disulfide or on silicon oxide. So comparing those 2 could be tricky, but still you have a flat template. So not sure we can comment much on roughness in this particular experiments.
Yeah. I see. Okay. Yeah, I mean, SiO2 is quite flat, but it is not as flat as boron nitride. And I think there are some differences. There are some very subtle differences. And again, I think those differences play a role electrically in these films, but I don't know if they play a role thermally. I really don't know. So that's where my question was coming from. Slide 45 and 46, could you go there? Right. So yeah, this is perfect. Okay. So I think I wrote down a question, but I noticed that I probably missed something on this slide. So my question here was, did you calculate the dominant phonon wavelength as a function of temperature? And I noticed that it's actually written on the slide. So it looks like you did. Is that what that is?
Yes.
Okay.
Thank you for this question, because I didn't really explain how we obtain these numbers. This is, first of all, the data normalized to the substrate, so the bare substrate value. So the bare substrate is 1, and is 1 across all the time delays, except for the early times where the signal changes more significantly, more abruptly. So therefore, we average these signals, we compare them to the substrates, we normalize them to the substrate. We make the absolute value of it, because actually this would go negative and then recover positive, but we just provide the absolute value here. And the fit is using an area function. So basically what you would use in a 𝗗𝗿𝗿𝗲 resonance cavity. So it's a transmission function with the area function, and we can retrieve the wavelength as we have how the thickness changes the amount of signal.
I see. Okay, I see. So that, yeah. Can you go to the, so maybe this is related to the next slide then. Yeah, I was trying to understand a little bit more about this transfer matrix model that you put together. Yeah, this went by a little bit quickly, and I wanted to pull it up again. So this is showing reflectivity, number of layers, 3 layers, 10 layers. Got it. I see. And again, you are using the wavelength that you showed in a previous slide in this model as well, correct?
No, this is not what this is. This is a complete separate kind of experiment. Well, it's a simulation where we study the optical propagation inside our multi-layer stack. So basically, we consider the thickness of all our materials, and we consider their optical properties.
Okay, so this is optical. Okay, I thought these were phonons as well. Sorry.
Yes. Sorry, we put phonon and photon interference. It is difficult to distinguish quickly. But this is purely optical simulation, where first of all, we get the reflectivity from the first top surface due to the presence of all the interfaces underneath. And we use the temperature dependencies of these optical properties to retrieve the thermoreflectance coefficient, the estimated thermoreflectance.
Got it.
We also get a sign change, so from negative to positive to negative again.
Okay, yeah, I thought this was a phonon interference simulation. So, but I missed the letter change, like you said. Okay. I don't have other questions, so I'm good. Thank you.
Thank you.
And thank you, Professor Bob. So I think it's my turn now. So, well, it's good for me to be the last one, because a lot of my questions have been already on the table. So that would make my life easier. I would like to start with the chapter 2 of the thesis. So when you describe the different thermometry methods, you make emphasize on the Raman-based thermometry and the unprobe thermoreflectance. But I was wondering, you didn't discuss photoluminescence-based thermometry. And I was thinking, for example, I don't know, like exciton peak shift, line widths, intensity ratios, and so on. And that I know that it changes for 2D materials. So like then I was wondering what I guess that you didn't discuss, because it's not a very powerful technique because of something. And I don't know, I wanted you to discuss like what will be the drawbacks of that and what are the advantages with the other techniques.
Thank you for this question because I think it's very relevant. I didn't discuss it because I didn't use it specifically in my thesis, but in the group we have used these exciton signals as a thermometer. So basically, because of the exciton line width, we can estimate the temperature increase in our suspended materials. And actually, this was very well written in the thesis of Sevin. And yeah, we can, of course, use it. There are other challenges, but the advantage, especially in our setup and in our lab, is that we can see with time how heat spreads and how it spreads along this atomically thin material. So it is visually, like you can estimate the diffusivity, and we also found many interesting observations which we are explaining with exotic types of heat transport. But here I didn't use any of these observables as a thermometer, and therefore I limited my discussion to the optical thermometers I used because I already had so much that I didn't even show in the thesis. Like, I had to choose very carefully what to show and what not to show. So this was very well discussed in Sevin's thesis.
And please accept my apologies because I got into the discussion mode already and I just jumped into the questions without acknowledging you for inviting me for being part of this committee. And I would like to congratulate you for the work that you have done. And I completely forgot, like starting with a polite way. I'm completely sorry. My apologies.
Thank you very much for being here.
Also, congratulations to your supervisor. I know how tough it is to start in an empty lab. I know how tough it is to start in 2 empty labs. Right?
I mean, I think it would have been way tougher if you wouldn't have reported so many methods and cheap techniques that we exploited to make this possible. So thank you.
Well, nothing to thank. I mean, like I value highly the work that you have done setting up not just the tools but also the techniques. I mean, like the know-how in a group is the most valuable thing, right? So you have done in the thesis. It's not just like the results that they are of the highest quality. That is for sure. That is completely clear. But you have also like set the techniques and tools and protocols that the other people in the group they're going to use in order to do the results. And that thing is one of the most important things that you have done in the lab for sure. And that puts the bar really high for your colleagues. Okay, so now they have to use it properly. Okay, now I will come back to the discussion more. Sorry for my emphasis in there. So I want to make a very specific question regarding the fabrication, the chapter 3. This is a test question. It's to check if you really did the things or not. Go ahead. So when you describe the PDMS fabrication in your thesis, could you clarify which surface of the cured PDMS you use when you cure it on the Petri dish? The one facing the air or the one facing the glass?
We use the one facing the air.
And why?
Good question. Yeah, because the surface facing the air has been in contact with oxygen, and therefore you are creating a very thin layer of silica.
Mm-hmm.
So basically you have a higher stiffness, which will help your 2D material remain flat, I would say. Of course, you could think that the bottom surface is flat, but we're using plastic Petri dishes, so I wouldn't expect they to be very flat.
Okay. Do you consider using oxygen plasma or UV ozone treatment to enhance this silanization process of the surface? Or
we did try. We started using this and even exfoliating on top of our PDMS. You can get maybe flatter and higher material quality, less wrinkled, strained flakes. but it would produce much smaller films. As you see here, I can produce millimeter size thin flakes. So it's just patience and repeating it one time and another time. Of course, yeah, I think it could help if you would optimize this process very well, but we had so many things in our plates to already go and see how long do I need to put this in the oxygen plasma to get better flakes. I mean, I'm already doing it enough so that I produce very nice flakes anyway, and we just skipped this step.
Okay. So I trust that you did the things. Regarding the addition of the flakes on the, so when you use this gold metallization of the silicon nitride membranes, okay? So you do that in order to increase the addition of the flakes on the membrane, right? So to make your life easy when you're going to transfer over the hole, I understand.
Yes.
Did you notice any difference between using like freshly evaporated samples and old gold, let's say, let's call it like that?
Yes, actually, we see a much better addition for freshly evaporated gold, and also maybe here it's not clear, but in the wrinkled slide, it is a bit more clear. Some blisters, whatever. Like if you use freshly evaporated gold, both the transfer will be easier, and the TTR measurements with transducer will also be easier and give more signal. Once the gold has stayed there for a while, the signal we get is lower, the addition and the transfer yield we get is lower. So yes, using fresh gold really helps.
Okay. Regarding these suspended samples, I was wondering about the tension, the strain they have, okay? Because when I see the AFM image that you have shown, like these kind of like flakes that they go under, you know, like they stick to the wall and they get flat. Usually when you measure mechanical properties of these kind of like membranes, they do have a big tension, no? So biaxial strain, usually.
I think this is true. You typically, when using small holes, you have a large tension, but our flakes we've shown using brillo-wine light scattering spectroscopy that the residual stress is pretty low. For some samples, it was kind of high, but most of the samples showed very minimal residual stress. And I think this is just because we have huge suspended areas, so the flake can just relax and remain flat. Maybe it's not flat, but it's a bit sagging. We will never know, probably. It will be tricky to quantify. But yeah, they conform very well to anywhere you put them. So if you press them against the hole, they will obviously like to stick to the sides of the hole. And I think just because of this, we have much flatter, much nicer regions, as we can show here. Maybe here, the conformal in the gold was not so good, and when we heat it up, it accommodates and produces a flat.
And when you measure the photoluminescence on the supported part on gold and on the suspended part, so if I recall it correctly, you have a, yes, you have, you have a blue shift. This is a figure 3.12, I think.
Yeah.
Yeah, you have a blue shifted PL's peak for the suspended. Blue shifted
in the suspended region.
Yeah, so
yes.
That is typically coming from biaxial compression, and that's why I was kind of like puzzled. No?
Could be. I never thought it that way. I would imagine that having them on the supported region quenches the higher energy part of this emission, and it's not really a shift, but more like these are coupled peaks of the different excitons, and one decreases and you are left with the other, which is a shoulder. I think it's kind of there in the figure.
So you think that is a neutral exciton to trion ratio thing?
Something like this.
Okay.
I think
that might be. Suspended part has lower doping than the supported part.
Exactly.
Okay. Makes sense.
Maybe not, we should do more experiments to confirm this. Maybe.
No, I mean, I didn't think about it. It's yeah. Also, like in this chapter of the suspended membranes, I was a little bit puzzled about the absorption of the single layer molybdenite for 532 nanometers, right? So yes, so it's like in between, yeah, it's around like 15% for the monolayer, no, the absorption.
Yes, one is like 9% and the other is 15 or a bit less.
Ah, okay, 9.
Yeah,
Okay.
these are two different samples, the two I showed here. These two different samples, they give slightly different values of absorption, but the reflection is basically the same. It's the transmission that changes a bit. It could be that when placing the samples or the control substrate that we place and do the correction, introduce a bit of error, or that the samples have slightly different doping, whatever, that would lead to slightly different.
So I was a bit puzzled about the large value of the absorbance, no? So because I was expecting something like that, like 10% at the exciton resonance, right? So like in the case of is molyselenite this one, no?
Yeah, this is of
So-
resonance.
No, it's 532 nanometers, right?
Yeah, and the
So the
resonance
exciton is at 700.
785 for the monolayer.
Yeah.
So we are of resonance, we are above the band gap.
Yeah, but that's why. So I mean, I will expect a smaller absorption than at the exciton level, right? So at the exciton resonance, I will expect around like 10% for the single layer. I was puzzled that this is also like.
I mean, there are other optical absorption measurements on transparent substrates that show values from 5 to 10 or a bit more. So there is a bit of literature there, but I think no one ever measured them without any interaction with nothing else.
No, that's for sure. I think like all the measurements they are done on transparent substrates or something like that, so not really suspended.
Yes.
Well, I mean, I was just puzzled about the value, but it is true that we cannot compare with the other experiments, though, right?
Yeah.
Ah,
We actually, to retrieve these values, we do linear power dependencies. So we change the power and they behave very linearly with power, which means that we are not changing non-linearly our observable. So yeah.
Okay, I'm going to skip some for the sake of time. Regarding the transducer layer for the thermal reflectance, I think I can admit that I have no clue about thermal reflectance. So maybe what I'm going to ask is very stupid, but so what would you expect if you do the experiment without this transduction layer? So I mean, like I guess that the reflectance of the transition metal like 𝐒𝐭𝐿 also changes with temperature. So can you do the experiment without cupping, or?
I think you could. There are some experiments doing transducer-less TDTR. However, our films are so thin that if you illuminate them, you would heat up the entire z-axis. So therefore, you don't have a thermal gradient in the out-of-plane direction. And therefore, you would be mainly looking at in-plane transport and coupling into the substrate, I would say. So it would be very difficult to retrieve an out-of-plane thermal transport.
So the transduction layer has to be opaque enough, let's say, but thin enough so you can still see the flakes.
Yeah.
Nice. See. I'm learning a lot. This is nice about physicists. Then I have a question about the interfaces and geometries, right? So because as you're transferring the flakes with PDMS, and PDMS is, I mean, as you can understand, I love PDMS transfer, but I'm also aware of the limitations of PDMS transfer, and it's not the cleanest transfer, so you can leave residues. How do the residues of PDMS can affect, for example, if you have residues on the clamping on the freely suspended layers, or if you have residues in between the flake and the silicon oxide in the reflectance TDTR
Yes.
measurements. So how that can affect the
I
measurement?
think this is a very important question. The point is, upon exfoliation, you're basically cleaving layers of your material, so the surfaces you reveal are clean. They have no residues. The surface that is in contact with the PDMS could have residues, and once you transfer it, you may leave some residues. We have seen suspended areas of our materials showing residues, and therefore discarded those samples. Obviously, we cannot perform AFM everywhere in the suspended region, but if we perform any kind of mapping on our samples using either the spatiotemporal or Raman scattering, we can very well see these things. Also, in the TDTR, we've shown that we are extremely sensitive to the layer number. Anything that changes slightly the thickness would massively change the signals that we measure. So we can see residues, we can see cracks, wrinkles, particles, everything. We will see it in our maps. So I would say, based on the homogeneity that we find both in TDTR and in Raman thermometry, our flakes are pretty clean.
I think I'm going to skip the rest of the questions, and I'm going to take the last chance that being president of the committee allows me to talk to you before you become officially a doctor. And if Professor Pop doesn't mind, I would like to do this in Spanish. Is that okay, Professor Pop?
Claro que sí.
Perfecto. El título de doctor es, como he dicho antes, el título académico más elevado que puede otorgar la Universidad Española. Y eso conlleva una serie de responsabilidades. La sociedad exige que te comportes con transparencia y que tomes tus decisiones basado en hechos, en análisis rigurosos y no simplemente en opiniones. Y tratar de aportar a la sociedad, en la medida de lo posible, el conocimiento que generes. ¿De acuerdo? A cambio de todos estos requerimientos, pues la sociedad, la Academia Española te da unos privilegios, que no sé si conocerás.
Creo que
Los doctores españoles tienen el privilegio de mantenerse sentados y con la cabeza cubierta en presencia del rey. Utilízalo con mesura, porque es un gran privilegio.
esto es serio.
Es totalmente serio. Por eso los actos académicos solemnes empiezan con doctores sentados y cubríos. And with that, Eric, I think we are going to close the academic part of the defense. I'm going to ask the rest of the people to leave. We have. It is true. Thank you. ¿Hay algún doctor en la sala que quiera hacer una pregunta? Is there any doctor in the room that wants to make a question to the candidate?
Or online.
Or online.
Yes?
Not sure if we could see.
So you have the chat there? No, there is no questions on the chat.
I'm not sure how to see the chat, to be honest.
Maximize it on the.
I think you have to maximize it in the corner in order to see the whole thing.
Oh, yeah.
No.
No.
Suerte, David. All right. So if there is no further question, I think we have to close the defense part. Vamos a cerrar el acto público de defensa. Les rogamos que salgan de la sala porque ahora el comité tiene que deliberar. Les avisaremos cuando terminemos la deliberación. So we are going to meet together now, Eric.
¿Sabes cerrar la relación?
Sí.
No.
Pero yo creo que tenemos que invitar. Yo al menos suelo invitar. Me parece apropiado preguntar.
El online.
O sea que se llama.